myself Dr. Bharti Patil, working as an assistant professor of physics in the Department of Physics, Maharaja Jivaji Rao Shinde College, Srigonda, Ahmednagar. We have started our chapter number 4 related to solid state physics. Its name is magnetism, and in today's lecture we are going to see ferromagnetic domains. In our previous lecture, we have seen that there are various types of magnetic materials such as ferromagnetic materials, diamagnetic materials, paramagnetic materials, antiferromagnetic materials, and perimagnetic materials. These ferromagnetic domains is related to ferromagnetic materials. In case of ferromagnetic materials, this material consists of the dipole moments, and there are the regions. I will show you. In case of ferromagnetic materials, there exist regions as shown in figure, and this each region is called as domain, and in this domain the magnetic dipoles are organized in this way. It consists of dipoles which are oriented randomly. So, what is ferromagnetic domains? In case of ferromagnetic materials, there are the regions which consist of the dipole moments which are oriented in particular direction, and each this region is called as domain. The volume of each domain is about 10 raised to minus 8 to 10 raised to minus 12 meter cube. Volume of each domain is about 10 raised to minus 8 to 10 raised to minus 12 meter cube, and the number of atoms present in each domain is about 10 raised to 17 to 10 raised to 21. It means that this large amount of atoms are located inside each domain, and each domain will have its own orientation, and these domains are separated from one another by a wall, and this wall is called as domain wall. This wall of separation of one domain from another is called as domain wall. This is the picture of the ferromagnetic material when there is no any external magnetic field applied. That is, in the absence of external magnetic field, the ferromagnetic material will consist of these domains which are randomly oriented. But when we applied external magnetic field, this is in absence of when there is no magnetic field. When there is no any external magnetic field is applied, you will observe this ferromagnetic material is like this. But when we applied external magnetic field to this domain or to this ferromagnetic material, then all these dipole moments will get organized or arrange themselves in the direction of, they will arrange themselves in the direction of applied magnetic field. And we are saying that material is magnetized in presence of magnetic field. So, in absence of external magnetic field, the picture will be like this, and in the presence of external magnetic field, the magnetic dipole moments will try to align themselves in the direction of applied magnetic field. Suppose this is the direction of applied magnetic field, then magnetic dipole moments will organize themselves in the direction of applied magnetic field. This is related to what is domain and what is domain wall. And suppose if T is the normal temperature, T is the temperature, that is ordinary temperature. At this temperature, the thermal agitations, that is the thermal vibrations which are produced at room temperature, are not sufficient to destroy this alignment of the domains. Therefore, at normal temperature or at room temperature, this alignment of the domains will not get destroyed, and hence, in case of ferromagnetic materials, if we applied external magnetic field, these materials will get strongly magnetized. Initially, it has been experimentally proved that suppose when we applied the magnetic field which is having low strength, then some dipole moments will get organized in the direction of external magnetic field, and their strength or their value will get increased as compared to the domains which are less originated, less aligned in the direction of applied magnetic field. It is experimentally proven, and hence if we applied the at room temperature, it is observed that the thermal agitations or the thermal vibrations are not sufficient to destroy this alignment of the domains, and hence even after removing the external magnetic field, this domain will not return back to their randomness. Therefore, they will have net magnetization even after net magnetization even after removing external magnetic field. So this dipole will get aligned in the direction of applied magnetic field, and hence they will have net magnetization. And if we observe the in nature, the ferromagnetic materials are very limited. Their numbers is very limited. Examples of ferromagnetic materials which will have ferromagnetic domain structure are nickel, cobalt, iron, and they will have their ferromagnetic nature at a low temperature, sufficiently low temperature. Then there are the group of rare earth materials like gadolinium, terbium, and these materials will have the ferromagnetic nature or such type of domains, ferromagnetic nature at a temperature lower than room temperature. And it is observed that at sufficiently higher temperature, all these materials will get converted into paramagnetic materials. at higher temperature, these materials will get converted into paramagnetic materials. So, as we increase the temperature of the ferromagnetic materials, the dipole moments will get destroyed and hence they will have less magnetic field or they get less magnetization, and hence at higher temperature these materials will get converted into paramagnetic material. The temperature at which ferromagnetic materials get converted into paramagnetic materials is called as Curie temperature. This temperature is called as Curie temperature. What is Curie temperature? Temperature at which ferromagnetic materials get converted into paramagnetic materials. At this temperature, they get converted into paramagnetic materials and it is called as Curie temperature. Then, if we plot a graph of magnetization produced versus temperature in case of ferromagnetic materials, then it is observed that these materials will have higher value of magnetization or called as spontaneous magnetization at a temperature T is equal to 0 Kelvin, as T is equal to 0 Kelvin, and as we go on increasing the temperature, then it is observed that this material will lose the uh, alignment of the dipoles and their magnetization will become 0 at a temperature called as Curie temperature. So, in case of ferromagnetic materials, at temperature called as Curie temperature, the magnetization will become 0 and this material will get converted into paramagnetic materials. So, let's revise what are domains in case of ferromagnetic materials. So, ferromagnetic materials are the materials which will get, if we applied external magnetic field to them, then they will get magnetized in the direction of applied magnetic field, and even after removing the external magnetic field they will not lose their magnetization. In case of ferromagnetic materials, there are these small regions in which the dipoles are aligned themselves in particular direction, and these small regions present in a ferromagnetic material are called as domains. Each domain will have dipole moments and the number of atoms or the volume of each domain is about 10 raised to minus 8 to 10 raised to minus 12 meter cube, and also the number of atoms present in each domain is equal to 10 raised to 17 to 10 raised to 21. Each domain gets separated from the another domain by a wall and that is called as domain wall. In the absence of external magnetic field, these domains are randomly oriented. Therefore, net magnetization is very less. But in the presence of magnetic field, these domains will get aligned themselves in the direction of applied magnetic field, and hence the material is said to be magnetized. At a room temperature, the thermal agitations or the thermal vibrations are not sufficient to destroy this alignment, and hence they will persist their net magnetization. But as we increase the temperature applied to these magnetic materials or ferromagnetic materials, then the alignment of the domain will get destroyed and hence they will lose their magnetization. The temperature at which the ferromagnetic materials get converted into paramagnetic materials is called as Curie temperature. It is observed that the nickel, cobalt, iron, they are having a ferromagnetic nature at sufficiently low temperature. Then gadolinium, terbium, they are also having ferromagnetic nature at a temperature lower than room temperature. If we increase the temperature applied to ferromagnetic materials, then they will get converted into paramagnetic materials at Curie temperature. If we draw a plot of magnetization produced versus apply temperature, then it is observed that as we go on, these materials will show maximum magnetization, or it is called as spontaneous magnetization at a temperature equals to 0 Kelvin. And as we go on increasing the temperature applied to this ferromagnetic domain, then it is observed that they will lose their magnetization at Tc, and this temperature is called as Curie temperature. Thank you.